Hello friends, in previous video we have studied a definition of ROCs as well as the types of ROCs. Now we'll discuss the properties of ROCs, but before moving towards the properties, we'll revise the definition as well as the types. Basically, what is the definition of ROC? A Laplace definition. Integration of minus infinity to infinity x of t into e to the power minus s t dt. This was the definition of Laplace transform. The important name is the product, which is x of t into e to the power minus s t. This product is integrated with respect to time t over the range from minus infinity to plus infinity. Now, if this integration produces a finite result, if x of t is any function, and after taking a product, and then we'll apply integration from minus infinity to infinity. If this integration, the whole integration produces a finite result, means what? The chosen x of t input is converted or transformed into Laplace domain from minus infinity to infinity. I'll explain you by taking one example. Now, the definition is integration minus infinity to infinity. This was the definition of Laplace transform. Now, we are going to replace or we are going to paste any different inputs over here. Or you can say we are going to consider different types of input that we have studied in the start of Laplace transform. There are basic elementary signals are there. Delta function is there, unit step, a ramp, exponential, sinusoidal, cosinusoidal. There are different types of functions are there. Now we are going to replace this x of t, or you can say that you are going to substitute this x of t value as a input. Now, after multiplying that input, let's assume the u of t is the function. So x of t is my u of t. So of course at this place we are going to place u of t value. Now if the integration of u of t, or you can say the integration of this product gives us a finite result. I'll repeat. If my x of t is my, let's take one example, unit step. Now if my x of t is a unit step, then if I take the integration, if I apply the integration on the product of u of t e to the power minus s t dt, if I apply the integration on this product, and if this integration creates or produces or gives us a finite result, which means this unit step can be transformed into a Laplace domain, or you can say you can represent this unit step function on S-plane, and the region of it is minus infinity to infinity. This unit step can be transformed into S domain, and its region is started from minus infinity to infinity because it produces a finite result. The integration produces a finite result. What do you mean by this? This function can be easily transformed into Laplace domain, and the region of u of t will be minus infinity to infinity, or you can say the integration of this is infinite. Then unit step cannot be transformed into Laplace domain, or you cannot plot unit step on S-plane. The region of conversion means what? This was the integration limit. This integration limit tells us about the actual region of function when it is transformed into S-plane, or you can say Laplace domain. So there are different properties are there which gives us an idea about basics of ROCs. What should be the place, what will be the limit, what will be the region of given function. There are different types we are going to study. First type was a two-sided, second one a causal, third one a non-causal. ROCs are classified into three parts. The first one is causal, means a right-handed signal. Means what? If the function is available, or you can say a function produces a finite result only in between 0 to infinity, the function produces a result, or if the function creates a finite result in the region, if the integration limit is 0 to infinity, then you can say that that given function will be transformed into S domain. I'll repeat. If the integration limit is 0 to infinity, I'm talking about right-handed signals, or you can say causal. If any function, now the integration limit is 0 to infinity. If I substitute any function over here, if we have an integration limit 0 to infinity, let's say the input is x of t, e to the power minus st dt is the product. Now, if this integration produces a finite result, then you can say that that function can be transformed into S domain, but the region of that x of t in S domain is always 0 to infinity. 0 to infinity means it is on the right hand side of S plane. That's why the function is referred as a called as a right hand signal or a causal signal. Similarly, if the x of t integration minus infinity to 0, this was the higher lower limit and this one is the higher, the x of t e to the power minus st dt produces a finite result, or you can say after taking integration the result of this is finite. Then you can say that this x of t can be transformed into S domain, but what should be the region? The region is always minus infinity to 0, means minus infinity to 0. This is the region of x of t because it produces a finite region, it produces finite result in the range from minus infinity to 0. This is called a right-handed signal or a causal, whereas this function is called as a left-handed signal or anti-causal, or there is one more name which is a non-causal. Now there is one more type which is a two-sided. In most of the cases, different types of inputs produces its result, but only in certain region, and beyond that region its result is always infinite, and within that limit its result or it produces a result which is finite. Means what I want to say, let's say this is the S plane. Now if one function produces a result only in one time limit, let's say from minus t1 to minus t2, only in this region this function produces or function will gives us a finite result, then you can say that that function is a two-sided because it only produces a result only in between region. After a region, like beyond the region, if you move towards the right hand side from t1 and if you move towards left hand side from t2, then that function will create infinite result. So that function is referred as, this type of such type of function is called as two-sided function. So basically there are three types. First one is a causal, where the integration, the function produces finite result only when the integration limit is 0 to infinity. Now if we take the opposite limit, that is from minus infinity to infinity, that function will create infinite result. Now let's move on to next. The second type is left-handed. This was the first, this was the second. If the function produces a finite result when the integration limit is from minus infinity to infinity 0, then that function is called as a left-hand side signal or anti-causal or non-causal, because it is available or it is transformed into S domain only on the left-hand side of S plane. Now the third part is two-sided. Now this function is only available in between the time period, which means you can say that if we move from minus t1 to t2, then it becomes a left-hand sided. If you move from minus t2 to t1, then it becomes a right-handed signal, which means it is a two-sided signal. But if you move right-hand side of t1, if you move towards the right-hand side of t1, then function will create infinite result. And if you move towards the left-hand side of minus t2, then function produces infinite result, which means the function only creates a finite result in between these two limits. That's why this function is called as two-sided signal. Now we will study the different. This was the basics of ROCs. Now we'll study the properties of ROC. Properties means if the function is a right hand sided or a left hand sided or a two sided, then what will be the place of ROC, and if it is transformed over the entire region of S plane, then what will be the plane or what will be the location of ROC, what will be the place of poles when it is transformed into S domain. We'll discuss all these stuffs one by one. So first of all, we'll go through the properties. Now students, now be careful. This property is always asked in exams. So please go through it seriously so that you can understand the basics of ROCs, where it lies, what will be the location for right hand signal, left hand sided or two sided signal locations. Now we will study a properties one by one. The property number 1. The ROC of X of S consists of strips parallel to the j omega axis in the S plane. Now we know that basically S is classified, or you can say a combination of real plus imaginary. Real is the sigma, whereas imaginary is j omega. Now whenever any function transformed into Laplace domain, then we will always mark one region, and this region is always marked by different parallel lines, or you can say the strips, and these strips are always parallel to the j omega axis, which means I'll tell you the example. Now suppose if any function, this is the sigma minus sigma j omega. Now let's assume here we have one pole, or here we have the pole which is after transforming any time signal into a Laplace domain, this is the location of that pole. Now this pole is stable, or you can say it produces a finite result, but when its region moves from t1 to infinity, when its region is available from t1 to infinity, this t1 is nothing but the location of that pole. Now how to mark the region? According to first property, we will always mark, let's say this is the pole, so we will always mark a parallel lines, which is, we will always mark a strips, and it is parallel to j omega axis, which means this is the region and these are the parallel lines, because the sample is transformed into S domain when we assume its region is t1 to infinity, and when its integration is produces a finite result between t1 to infinity, then we will always mark one ROC for it. So its ROC always represented by a strips of parallel line from j omega axis. Now we will study a property number 2. Now the property number 2, if x of t is finite duration, finite means bounded or limited, and is absolutely integrable, which means the integration, after taking integration you will get a finite result, then the ROC in the entire S plane, which means let's assume the definition of Laplace transform, which is minus infinity to infinity x of t e to the power minus t was the product, and we are going to integrate this product with respect to time t. Now if this product, or if this integration produces a finite result, which means that input x of t can be transformed into S domain, but what will be the ROC range? The ROC range is from minus infinity to infinity. I'll show you how. Now according to definition of Laplace transform, minus infinity to infinity x of t e to the power minus st dt is the definition. Now if this product, or if this integration produces a finite result, which means you can transform this x of t in Laplace domain, but the region of that x of t is always from given limit, is always from minus infinity to infinity, means what? It is available over the entire region of S plane. This is the location of sigmas. This is the highest right-handed side limit, and this is the highest leftmost limit, and here we have j omega. I'll repeat what I said. If this function, if this integration is completely integrable, integrable means what? If this integration produces a finite result, when its range integration limit is from minus infinity to infinity, this range always gives us the region ROC limit when the function is produces a finite limit. Here this product is integrated over the range from minus infinity to infinity. After transforming this function into Laplace domain, we will always place that function in between limits, or that function is available in between region. Now, what will be the location of region? What will be the value or limit of that region? That limit is always the integration limits. Now, if this integration produces a finite result, which means this x of t can be transformed into Laplace domain, and what will be the region of that function? That region is minus infinity to infinity, which means according to statement number 2, property 2, if the function produces a finite result, or you can say it is a absolutely integrable, which means it produces a finite result, then as if this function is integrated from minus infinity to infinity, which means after getting a finite result, you can say that this function can be transformed into Laplace domain, and the region of that function is minus infinity to infinity, which means it covers the entire region of S-plane. So S-plane is nothing but this was the whole S-plane, and if from minus infinity to infinity it produces a finite result, which means I will draw a parallel strips which covers the entire S-plane. This was the statement. If the function is absolutely integrable from minus infinity to infinity, then that function is available over the entire region of S-plane, and to represent the entire region we will always mark as parallel strips. Now we will study a property number 3. Now the property number 3 is, if the x of t is right hand sided, which means the function is available on the right hand side of time period, and if the line passing through a real part of s is sigma naught. Sigma naught is nothing but the polynomial of root. Now we know that whenever we want to plot a pole zero plot, we will always try to find out the roots of that equation. So after finding the roots, we will always have one s term, and that s term is always there with the one polynomial. So that polynomial is nothing but my sigma naught. Now I'll read this statement once again. If the x of t is right hand sided, and if the line passing through real part of s is sigma naught, this sigma naught is in the ROC, which means the function is right hand sided, means the ROC is available on positive sigma, or you can say from 0 to infinity, and if the line is passing through sigma naught and this value is in ROC, then all the value of s for which real part of s is greater than sigma naught will also will in ROC, which means I'll tell you. Now let's assume my function is x of s is equals to, let's say it is 1 upon s minus 2. This was the my pole. Now how to find out the location of this pole? Just equate this denominator with equal to 0. So s minus 2 equal to 0. So what you will get? S equals to 2. This is the location of pole. Now we will plot a pole 0 plot. Now I'll place this pole value on my S-plane. We know that this is the value of positive j omega. This is the axis of imaginary axis, you can say. Now here we always plot a real value of s if the value is positive. If the value is negative, then we will always mark it on left hand side of S-plane. Now right now my s value is 2, which means this s is nothing but it is always sigma plus j omega. Now this value is real, it is not a complex, which means j omega value is 0 and sigma value is 2, and this you can say that sigma is the real part of S, where j omega is the imaginary part of S, which means the real part of S is 2, or you can say that the sigma value is 2. In statement, what we have written? The sigma naught. So you can say that this is the value of sigma naught. Now, what I said, if the pole is placed on the right hand side, which means let's say this is the value of pole and it is on right hand side of S plane. If its ROC is on right hand side, and if the real part of S is equals to 2, which means the pole value is 2, then its ROC is available on the right hand side, and this ROC will cover the values which is greater than sigma naught, which means if the poles, if the system poles are there and if the values of that poles are greater than 2, then that all the values can encountered in this region. Now, what is important? In this case, the statement was if the x of t is right hand siding and if the real part of S is equal to sigma naught, if the real part of S is equal to sigma naught, then the values of S which is greater than sigma naught can be counted in ROCs. So look at here. Here the value is positive, which means our pole is on right hand side of S plane. This was the S plane. This part is right hand side. This part is left hand side. Now here the pole value is 2, which means the pole is placed on the right hand side of S plane. Now the next important part is here the real value is positive. That's why I have marked it on real axis. Now much more important is the region, as the pole is a right hand siding, which means its ROC is moving towards the infinity. Now the numbers, the pole value which is greater than 2, or you can say the real part of S which is greater than sigma naught, that sigma naught is 2, that all the values can be encountered or can be present or can be marked in a region of convergence. So if the values of S is greater than 2, that can be counted in region of convergence, or you can say that can be transformed into Laplace domain. Now we will study a property number 4. Now property number 4. In previous property we have studied a pole which is a right hand sided. Now in this property we will study a pole, now it is placed on left hand side. So let's start. A property number 4. If the x of t is left sided or left hand sided, and if the line passing the real part of S is sigma naught and it is in ROC, then all the values of S which is real part of S is less than sigma naught will be in ROC, which means, what do you mean by this statement? Right now my sigma naught is available on left hand side, which means the value of pole is negative. Now for negative pole, the ROCs always exist on the left hand side of that pole. Now the values of pole, or you can say real part of pole values, which means now all the values of poles less than the negative value of current pole always exist in ROC or can be converted into a Laplace domain. I'll tell you by taking some example. So let's go through the example to understand this concept or this property number 4. Now let's take one example so that you can understand the concept of property number 4. Let's say my x of S is having one single pole and the value of single pole is S plus 2. Now we will calculate the location of this pole. So for that we have to equate this root, or you can say this factor, equal to 0. So S plus 2 equal to 0. So what you will get? S is equals to minus 2. Now S is equals to minus 2. Just replace this S by sigma plus J alpha, which is the definition of S, and this value is 2. Again here the minus 2 is the real value, which means sigma naught, or you can say sigma value is minus 2 and the j omega value is absent, so its value is 0. So therefore you can say that a real part of S or sigma is minus 2. Now this value always plotted on left hand side. So let's draw one, I'll draw one S plane. Now our pole value is minus 2, so I will mark minus 2 over here. Now as this pole is left hand sided signal, which means this function ROC or the ROC of this X of is always available on left hand side. So ROC is always marked by parallel strips. Now if if we have one more pole which is S plus 5, of course this value is, if of course the location of this pole is minus 5 and this minus 5 is less than minus 2. As the minus 2's, look at here, as this minus 2 having ROC on the left hand side, now this minus 5 is lesser than minus 2, which means no need to find out ROC for minus 5, because according to statement the minus 5 having ROC, having a similar ROC, which is marked for S equals to minus 2. If the pole is placed on left hand side and if the another pole is there which is also having a value which is lesser than the present pole, now the current pole is minus 2. Let's say this is the value of sigma and this is the value of sigma naught. If the sigma naught value is less than sigma, then the real part, or you can say the ROC for minus 2 is marked on left hand side. So the similar ROC can be plotted for sigma naught which is lesser than sigma, because according to statements, if the sigma value is greater than sigma naught, or you can say the sigma naught value is lesser than sigma, then this minus 5 will also follow the similar ROC. So for ROC of minus 5 is left hand sided. Now we will study property number 5. Now property number 5. If the x of t is two-sided, two-sided means what? The function is available between the region, and outside that region the function or integration will have or will produce infinite, or you can say that function cannot be integrable. Now two-sided means what? The function is available only in two regions, in between two regions. Outside that region the function value will create infinite result, inside that limit will produce a finite result. Now we'll move on to property. If the x of t is two-sided and if the line passing through real part of S is sigma naught is in ROC, which means one pole is there and that pole is present inside that ROC. That ROC is a two-sided. Two-sided means it is available perfectly in between, and the place of that pole is perfectly placed in between. Then the ROC will consist a strip in a S plane that includes a line passing through real part of S is sigma naught. I'll tell you the meaning of this by taking one example. Let's go through the example first. Just go through this example. In this function we have three poles. First pole, we'll find out the location first. First pole is placed at 0. How to find out location? Just equate all the factors equal to 0. All the brackets will equate to the 0. So first S is equal to 0. So location of the first pole is origin. Now I'll equate second bracket equal to 0. So what you will get? S equals to plus 2. Now third bracket I will equate to 0. S plus 2 equal to 0. So what you will get? S equals to minus 2. Now I will plot pole 0 plot for the poles. Minus sigma, sigma, this is our j omega axis. Here we have minus j omega axis or a minus j omega value. Now I will randomly place all these values. The origin is always fixed. This was the origin. Now one pole is at plus 2, second pole is at minus 2. Now what was the statement? If such type of function is a two-sided. Two-sided means what? The function is having ROC in between. Now Two-sided means the minus 2 is stable or produces finite result from minus 2 to infinity, whereas this pole produces a finite result when its integration limit is 2 to minus infinity. So according to both these stabilities, these two poles are stable, or you can say creates a finite result when its integration limit is from minus 2 to 2, which means this type of system is a two-sided system or two-sided function or two-sided signal. Now one more pole is there, which is S, and now this pole which is at origin, this pole we have to calculate the ROC for the same, as both the functions produces a ROC and this ROC is the two-sided, and in that this pole is placed perfectly in between. Then the ROC for this pole is similar, which means there is no need to calculate the ROC for this pole. This pole is already stable because this pole enters or encounter in between minus 2 to 2. So this is the statement of property number 5. The short conclusion is, if any one of the pole value is exist in between two-sided signal, then no need to calculate the ROC for the same, because it lies or it encounter in between the ROC. So which means this pole is already considered as a stable pole, or you can say, if you want to find out the ROC of this pole, then the ROC of this pole will produce a finite result. Now we will move on to a property number 6. Now the property number 6. If the x of s is rational, x of s means what? The x of s is nothing but x of t is completely transformed into a Laplace domain. Then we can say that the x of t can be represented by x of s, and this x of s is the rational. Then its ROC is bounded by poles or extends to infinity, which means this ROC, a rational means if we have a numerator value as well as denominator, you can say that x of s is the function of x of s is s plus 2 in the numerator, and in denominator we have a s minus 2. So we have a rational number. Now for this type of rational numbers, the ROC is bounded by poles or extend up to infinity. Basically ROC is always calculated using a pole values. So there is no use of numerator. Numerator is useful while designing the filters. Basically finding a causality or anti-causality or a two-sided function, the poles are important, or the location of poles are important. Now so for this type of functions, for rational type of functions, the ROC is bounded by poles. Bounded by poles means what? The ROC is totally depends on poles, and that pole value can be extended up to infinity. So that infinity can be either positive side or can be negative side. Now we will study the next property, that is property number 7. Now property number 7. The x of s, if the x of s is rational, then ROC does not include any pole of x of s. In previous property what we have studied, the function x of s is rational, then the ROC extends up to infinity or up to pole, but pole is not counted in it. So look at here in property number 7. The x of s is rational, then ROC does not include any poles, which means if we have a 3 poles, all the poles are positive and placed in a sequential manner. Let's say the pole value is 2, 3 and 4. So the ROC of such type of pole is always exist from right hand side. ROC always exist on right hand side of rightmost pole, whereas leftmost pole will not be encountered, as well as that fourth value is also not counted in it. Now similarly, if we have a left hand sided pole, let's say minus 2, minus 3 and minus 4, so ROC is available on the left hand side of minus 4, whereas minus 4, minus 2 and minus 3 also not counted in it. Now we'll move on to property number 8. Now in this property, we have to, it is mentioned the x of t is right-handed signal, means all the poles, or maybe a single pole is there, that pole is placed on right-hand signal, right-hand side of S-plane, or the number of poles are given in function, all the poles are placed on the right-hand side of S-plane. That's why the function is said to be a right-hand sided. Now, then the ROC in the region in S-plane to the right-hand side of rightmost pole. As I told you earlier, if we have a 3 poles and all the poles are placed on right-hand side, let's say 2, 3, 4 are the location of poles, then for such type of cases, the ROC always present or always marked on the right hand side of rightmost pole, which means right now my pole value is 2, 3 and 4. So my ROC is right side of rightmost pole. The rightmost pole is 4. So your ROC is available on right hand side. But in that case, these 3 poles are not counted. Similarly, with the left hand side also, if we have, this was the next property, property number 9. I'll tell you the actual concept by taking one example. But first of all, we'll go through the properties first. Now, if x of s is rational, once again the same, and the x of t is left hand sided. Now, in previous property, it was right hand sided, right now it is a left hand sided. Then the ROC in the region of S-plane to the left of leftmost pole. So, I'll tell you the concept by taking one example. Let's go through the example first, so that you will get the idea what is mentioned in property number 8, 9 and 7. In the property number 7, 8, 9, what is mentioned? If you have a poles, if we have a poles and that pole value is, let's say there are 2 poles, x of s is equals to 1 upon, these are the 2 poles. Now, location of this pole is, just equate this value with equals to 0. So, s minus 2 equal to 0. What you will get? S equals to 2. Similarly, you will get 3. So, I will plot the pole 0 plot for the same. Let's say this is the location of 2 and this was the location of 3. Now, according to property number 7, the ROC always marked on extreme side of pole. But in that ROC, this pole will not be counted. In property number 8, it is especially mentioned if the function is right hand sided. Right now the function is my right hand sided and all the poles are placed on positive real axis. ROC always marked on right hand side of rightmost pole. This was the rightmost pole. So ROC always marked on right hand side of rightmost pole. But these 2 poles will not be counted in that ROC. Similarly, with property number 9, let's assume the x of s value is s plus 2, s plus 3. So, according to finding a pole location, we'll equate this bracket equal to 0. So, we have a minus 2 and minus 3 value. I will place both the values. Let's say this is the pole value minus 2, this is the place of minus 3, which is a pole. Now, according to property number 9, what is mentioned? The ROC always available on left side of leftmost pole. This was the leftmost pole. Then the ROC is available on left side of leftmost pole, means what? Over here. But these 2 poles will not be counted in that ROC. This was the property number 9. These 2 ROCs are similar. These 2 properties are similar. Only the thing is, here the ROC is available on right side of rightmost pole, whereas here the ROC is available on left side of leftmost pole. Now we will study basic numericals on this ROC, so that you can understand the concept of ROC by going through these such a few examples. We'll solve some examples in next videos. So thank you for watching this video. Subscribe Ekeeda and stay tuned with Ekeeda for further more videos. Thank you so much.